worked on years ago was books called Taquito Robot. Who's heard of the Taquito? Couple.
I've seen those.
This is a cool project. It's a six-legged walking robot. And basically it's called Taquito. It's like a stick mosquito, kind of a coin of words. That uses nitinol wire to actually move these six legs around. Very small walking robot. The book actually contains in it, which this one did, I took it out already, all the parts required to build your own Taquito robot. You have the plastic, you have the memory wire, piano wire, everything inside of there. So I've got the two books. I'll pass these around so you can see the two books. That's the beginning book and the advanced book. And tonight's prize is a brand new, unopened copy of the advanced book from my own personal set. I had bought a couple of these years ago when they were going out. So I'll pass this around. And if you remember tonight, let me know. We're planning to be a member team now the next month. Take you on your honor on that. The name goes in the hat. You can sign it to win this tonight. I already got a project for next month already to give away next month as well. And I'll pass these. I'll hold on to this one here since you can't open it. I'll pass these two around people to look at and see those. That's basically my spiel about IEEE tonight. Also, as Brianna was saying for the meeting, there's also senior members. How many people are senior members for IEEE? Any senior members? Got 3 of those. Senior members are those that have been in IEEE that have, I think it's 10 years, 15 years of industry experience, 10 years of industry experience, and 5 years of significant experience. So there are 3 of those here in the room already. But if you think you fit those qualifications, either are a member or plan to become a member, then talk to me, talk to Mary Ellen tonight, because they actually put together a drive this year. Actually, the next one's a month away. The next voting, but actually there's a voting to determine who gets in and who doesn't get into that set. So if you're interested in that, talk to her tonight. Get you signed up for that as well. And she can tell you how to get that all done. So any questions on IEEE before we go any further?
You don't have to have been an IEEE member during that time to be a senior member. You just have to be a member when you're reviewed for senior member. So you join, you can immediately go there.
Here's another reason I'm pushing IEEE membership. Not only because I think I should, but one of my goals is to find the person to replace me starting in January. I need an IEEE member for that. So the bigger pool I have, the bigger people we put in position to stand up and do what I'm doing right now tonight, which is announcing our speaker. The IEEE chair needs to be voted on between now and end of the year. Elected by January 1. Public reporting. My goal is, a couple people I have in mind, I want to come and look at the volunteers tonight. I'll tap them on the shoulder tonight. Look at a couple of members to willing to take over and run for office. So if you're interested, let me know. Before we get to tonight's talk, mention next night's talk. Next month we're having Daniel's talking about the robot operating system, which is a really cool open source package for connecting multiple computers together. We're doing vision, touch, all kinds of different sensors. We're using this as part of the Humanoid project the last few months. We're very impressed with what's done with that. We're presenting that next month. It'll be November, first Monday of the month, next month. Any questions for that before I move on? Good. Our speaker tonight, Dr. James Conrad. I first met him. It was actually working at Erickson and working at State Campus as a professor here a little bit, teaching a few classes. And then became a full professor here for a while. Weren't you? Take these several courses you were teaching here on State Campus. Went to Charlotte to teaching there. I was wondering, Charlotte, they don't have an embedded system program. Well, now they do. That's an embedded program, natural robotics program. I've been following something you've been doing there. Very impressed with his work with you there. He's also missionary that Mary Ellen is the director of the Region 3, which is all Southeastern U.S. IEEE. This year, James Conrad is director-elect to be as the director next year for IEEE.
Actually, year and a half.
2016. I had my years off. Okay. Oh, okay. Okay. This is 2016. So, welcome to the floor.
Former member of TAR. Actually, you never Stop being.
He's still in the middle of this, because
I'm still on the mailing list.
Yeah.
That's how I knew I was talking today.
Because I emailed him, and she emailed me back to that. So I was probably someone else. Go through the sheet, sign it up, check where you remember or not a member, and we'll have a drawing at the end of the presentation. Thank you.
All right, so as was mentioned, I'm, in fact, I've got this in my talk, and I'll show this as well. I'm right now a professor of electrical and computer engineering at University of North Carolina at Charlotte. It's a small university. It's only 27,000 students. Our program in electrical and computer engineering is approximately 750 students. And interesting enough, when I first started embedded systems at UNC Charlotte, I had 15 in my class. This semester, I have 100 students in my embedded systems class, of which 77 are graduate students. All right, so I'm going to talk about quad rotors, and mini quad rotors at that. And these aren't the micro ones that you've seen, you know, that you can hold on your wrist and flick it off and it flies around and comes back. But it's relatively small. In fact, if my hand model over there could hold it up and show it, then I'll be able to pass around, let you look at, be very gentle on it though. The other one is what a senior design group has worked on. I prefer that not be passed around because I actually still need it to work quite a bit when I bring it back. This is the second time that quad rotor has been to Raleigh. The first time one of the senior design students flew it, this was in like early April, and promptly broke the entire thing. And his team was so angry with him because, you know, senior design expo demonstration was the first week in May, and this thing was in a crumpled heap of parts. They actually made the student all the parts to fix it back up. But you know, quad rotors are dangerous. There's a lot of danger involved in it, and let me just give you a good example of some of this danger. Oh, the other way.
Dangerous. It sort of grabbed its own control and ran.
So what happened is, got a brand new quad rotor, had a student working on it. He was downloading some new code to it, and I told him, under no circumstances are you to take that outside. Practice, fly it inside to make sure the code is correct before you take it outside. If you do take it outside, use a tether. So, after the first download of code, and he quickly walked outside, not to my knowledge, or definitely not to my request. He started manually flying it, and you know, the controller didn't fly away. The whole thing flew away. In fact, it hit what we figured was a bug, and I think we identified the bug. Actually turned off communications with the controller and put it in a loop such that it just kept on going up. And the students said, it flew a mile in the air. And the prevailing winds at the time took it away from our building, towards the edge of campus, perhaps off campus. And eventually these things run out of power, and I have no idea where it landed, and to be honest with you, I'm not really sure I want to know where it landed, for fear of where it did land. We did post a couple of these signs in some of the buildings at the edge of campus, and we never heard anything from it. So that's the danger. You can lose them. So today, I'm going to talk about some quad rotor research that we've been doing. But first of all, you probably want to ask, who am I? I was given an introduction, but I actually have my my master's and PhD from this university, ECU department, which is in another building, I think, right? And I got my PhD in '92. I've worked at two small companies, IBM and Ericsson. You might have heard of them.
Small.
Yeah, small. I've also worked for two startups, both of which went out of business. So, yeah, that happens. And then three universities, University of Arkansas here, I was an adjunct faculty member, and I actually taught for 6 years. And then I've consulted for companies like Necton Research, which is iRobot, Emerson, and others. So, do I know stuff about robotics? Yeah, I know a little bit. In fact, here, I'll show you, Rodney, you didn't mention this one. So, the books that are being passed around are how to build this manual controlled robot called Staketo. Well, this is the third book and third iteration of that called Staketo Control. And so on it is, on the top is a TI MSP 430 processor, pre-programmed with code, and if you want to, you can download new code to it. It walks on its own. But what's the one thing you noticed about this as this robot walks? It's slow.
Yeah.
What else?
Big battery.
Big battery, right? Well, you know, anytime you look at robotics, that's the big defining factor of everything is power, right? And in fact, how much power does it draw? How much power does, you know, how much heat does it generate? But with respect to this, you know, I was getting tired of working with these robots that were really, really slow. You know, I wanted something that, you know, I want something that gives me more immediate feedback. So I wanted to work with something bigger. So I also have done some work with a much larger one.
There you go. 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 Drive it.
All right, so I admit, this is a really big remote controlled car, right? And this is the first step to make it autonomous, because we wanted to make sure, I wanted to make sure that you know, we had the control mechanisms working with this before we started adding on other types of control and obstacle avoidance and stuff like that. And yeah, that's pretty neat. This is what, a $7,000 all-terrain vehicle, and it really freaks people out to see it. Notice I have some LiDAR up front. We actually gathered data as it was running to see if it would be able to do optical avoidance. It could. We had GPS to determine if we could follow waypoints. You could. A couple of special modifications to it allowed us to control the throttle and basically tap into the engine control unit. We also got, we put on a brake, and we also were able to control the steering using the cameras. And those are pretty neat, but you know what, in the end, if you want to work with a robot that is both inexpensive and moves fairly decent, really what it comes down to is a quad rotor is an ideal thing. You know, these little Lego Mindstorms, they're still $350, and it's not all that into it, or you know, there's not that much ingenuity that goes into it. So we have purchased a whole bunch of $500 quad rotors, which will allow us to hack into most of the systems and identify how to fly, or how we can work with it. So, okay, just quick little background where I come from. I worked on a couple of products. Hey, look at this. We actually had a three-dimensional printer in 1996 that was, you know, relatively low price. It was only $40,000. Compared to what was offered at that time, the cheapest one was $400,000. Not bad. I think they've come down in price a little since then, haven't they? And then I worked for a small company called, as I said, Ericsson, working on a couple of phones as well. But the interesting thing is that if you think about how you do research or how you investigate products or anything else, usually you go through a couple of iterations. So for the Staketo control itself, it started out with one student doing a version of it that used the basic stamp.
and I worked with him on the design. I worked with a senior design group here at NC State, and that's where I discovered the MSP 430. Actually, they showed it to me. And then we came up with another iteration until the final iteration that is now out with the keto-controlled book. And when you buy the book, it still comes with the robot kit inside, including that microcontroller board. Now, I'm starting to build up my work in quad rotors. And so right now I have only 4 papers, and some of them are rather interesting, but I want to key on one technology or one aspect of this, and that is my main research question. Can you use image processing to maintain a swarm? Now, you've seen probably this video before, and I'm just going to show it to you because it's something that I'm sure you have seen at some time. And at the University of Pennsylvania, they have these relatively small quad rotors. And you notice that, oh, look at this, they maintain a really nice formation, right? Now, how could they do that?
Cameras surrounding them.
Yeah, they have a whole bunch of cameras that are shining down, and they have one system which is taking all of these cameras, and they're able to identify where it is, and a central system is directing the quad rotor which way to go. Now, imagine the problem associated with, let's say, a building that has just suffered a catastrophic collapse due to an earthquake. Do you have the advantage of lots and lots and lots of cameras inside to direct the quad rotors where to go? Do you have the advantage of maybe a really good Wi-Fi infrastructure inside to be able to relay information? Because you know radio waves go really good through concrete, right? And steel.
Structural steel.
Structural steel. Oh yeah, really easy to get through. So that's sarcasm, by the way. Yeah, right? So the question is, how do we get a whole bunch of these quad rotors to move in unison when there's no overreaching camera to tell them where to go? And the answer is, you have to know where all the others are. Now, can you do that easily with radio frequency? Not really, because radio frequency, first of all, the wavelength is extremely small. The computation needed to determine where it is, and you need multiple points. So it looks like video is probably the best way to go. But there's a problem. If you're in a building that has just collapsed, there's no light inside most likely. How do you know where anything else is?
Infrared.
Infrared. So imagine this. Imagine we have a set of beacons associated with each quad rotor flying. So a couple of infrared LEDs. And then the quad rotor has a camera on it that is able to detect these bright points of light. Based on what it perceives as the size of those LEDs, or for that matter, the distance between two of these LEDs, it can identify the distance that the quad rotor is from the beacon, which may be, in this case, we may have a single quad rotor able to see 4 other quad rotors or some other type of beacon and instruct everybody to maintain a particular distance. So the assumption is that each one of these quad rotors also has Wi-Fi or some other type of wireless mechanism, that this quad rotor here can actually give directions and say, move away from me half a meter. Come closer to me 1 meter, you're too far away. Or we're all about to move in this direction at the speed of half a meter per second. And maintaining this type of swarm or this type of formation will be important for some of the problems that we're going to be looking into. And I'll get to that towards the end of the talk when I talk about the motivation. So as I said, what do we want to do? We want to have a quadrotor system designed with onboard processing. No camera looking down. The flight algorithm for motion planning is going to be expanded for the swarm. And at this point, we're just starting with a solo quadrotor in autonomous flight and then maintaining its distance from a particular beacon. And so my instruction to them is to validate that this concept works. I want to put a beacon on my back. And I want to, yeah, that's a dangerous thing, right? And I want to walk and have that beacon maintain a 6 feet distance from me. Yes, sir?
Are you doing any slam techniques?
We are not doing slam yet. But that's the next step after we identify in fact, I have some students starting to look at that as well.
Is SLAM an acronym?
Yes.
SLAM is simultaneous localization and modeling. Oh, is that right?
Mapping.
Mapping, shoot. That's it. I've had too much beer today, sorry.
Could apply it.
A map is a model of geography.
Great, yeah, that's a good point, yeah, and mapping, sorry. So, so again, we're developing a base for the swarm application so that we can have perhaps different payloads. Because as I showed you earlier in this formation, and this is with quadrotors in general, you do know that it has, in fact, go ahead and pass that one around. You know that it has a limited amount of payload because with the more weight you put on it, the less time it actually flies. And oh yes, I took the battery off of that one just for the mere fact that I didn't want anybody to, kind of get any wise ideas. And so if you add additional sensors to a particular quadrotor, you're going to add to the payload, the weight, to the need for more batteries, more flight, on and on and on. So what if, for example, in this formation, we had a forward-facing camera that would be able to relay information back to a base station? What happens, or would it be nice if every so often we could have one of these quadrotors actually land and serve as kind of like a node to allow communications to hop through a building that doesn't have the ability to do communications because of the infrastructure being destroyed. So in other words, we're using this concept of a swarm to create, let's say, Hansel and Gretel's breadcrumb trail through the forest. So we're dropping little breadcrumbs, which are our quadrotors. And once the quadrotor is no longer flying, the consumption of energy greatly drops. You're familiar with how much one of these motors actually draws?
It's 15 amps to 30 amps.
I got a really good motor. It draws only 10 amps per motor. And that's at peak. So, 40 amps of current draw really drains the battery very fast. In fact, that quadrotor right there drains a battery in 15 minutes. And it's a big battery.
And typically the battery weighs more than the whole quadrotor.
And the battery does weigh more than everything else. We've done something a little bit interesting, to put it. How many of you have a Wiimote or Wii remote, right? Inside a Wii remote is a small camera. And it is specifically has one task, to look for 4 infrared dots in an environment and return those positions. So if you can imagine, see if I can pull this up. If you could imagine, if we were to create a beacon like this with 4 infrared LEDs, our camera, the Wii camera, that we take out of the remote and we put on our quadrotor, so you'll see it as it goes around, actually returns to us at a certain frequency the locations of each one of those, and based on the pixel location of those and to some respect the size as well, we can tell how far away that beacon is from the regular image. Okay, you didn't tell me how long I should talk. How long should I talk, Rodney?
How long you want to call?
I don't want to go too long, because otherwise the people are going to go, oh man.
Fine.
Yeah, don't worry, you know where it's near that point yet.
Okay. Yes, sir, question?
So is it sending out 4 infrared beams and then detecting where the ducts are in the environment? Is that how it's working?
Well, the
distance?
The beacon is something completely separate from the camera. So all the beacon is doing, it is a surface, and I should have brought the beacon with me, but it is just a surface that has 4 LEDs on it. So imagine literally, wow, look at the size of this chalk. Wow. All right. So literally I have a piece of press board or some other board like this, and I have put 3 LEDs in a row and then 1 below that LED. And it is about this size. The LEDs aren't that big, because that would be really big LEDs. Wouldn't it? So just a regular T1 3/4 infrared LED, which you can't see by the naked eye, but if you were to take your cell phone, you would be able to see it. And now imagine this. Let's look at the physics, right? If I'm standing here, and this is my field of view, I can see these are a certain distance. Now if I were way over here in this field of view, you would notice that the points all the way on the side are closer together, right? And actually, since I'm at an angle this way too, it would appear as the 2 this way are closer together versus the middle one and the side one are a little bit further apart. And using that, you're able to use just simple algebra to determine not only where the camera is looking at this from distance, but also what angle. And of course, it could be up and down too. Yes?
This isn't a flat object, though, is it?
This.
The light where the lights are coming.
Yes.
It is.
It is just right now it is just a board. If we were to mount it on another quad rotor, it would be literally on a piece of plastic as well.
So they'd have to like stay aligned. What if the quadcopter got offline and they couldn't pick up the infrared? You see what I mean?
Yeah, well, that's part of the problem that one goes into when they look for recovery from research, right? Knowing where you were previously and seeing if you can get back to that previous space. Because, for example, good question though, if this is one quad rotor and this is the beacon, and this is the quad rotor, and it was looking in this direction, and it was going in that direction, and then suddenly it no longer sees that, the obvious choice would be, well, let me go back to where I was to see if I could recover the signal. Question?
So with 4 beacons like this and 1 camera, you're able to recover relative position pretty precisely, and I'm guessing the precision goes up as you get a better camera?
Precision goes up as you get a better camera, but as you can imagine, you look, it's monochrome, so it's a really simple camera. The other advantage to this is, see the camera has built into it the algorithm to return the 4 brightest lights. So I didn't write the code to find the 4 brightest lights. It was already provided by, was it Nintendo that sells the Wii, right? Right, answer your question?
Thank
yes,
you.
sir.
So, did you say just a minute ago that your center dot is not precisely in the center?
No, it is.
So
The center dot is in the center.
So how are you using, what relationship are you using to determine the oblique angle?
Well, I mean, as you can imagine,
Relative delta X.
It's the
this is held
perceived.
at 90 degrees to you.
Yeah.
If I were to turn this a bit like this,
Yeah.
your perception would be that this is closer to each other very slightly, and this is
So
longer.
you're looking at the size of the circle.
Correct.
Okay.
not only the size, both the size and the relative distance. Because, don't forget, this is closer to your camera, and this is a little bit further away, and this is even further away.
It's the relative perceived distance that you have, not of what's actually on the
Right.
Well, the
board.
vertical distance would remain the same, but the side distances would.
Unless you go down.
Unless you
If
go up or down.
or up, then the.
So how do you
and-
determine-
And then, of course, as you're looking in the field of view, if the whole field of view goes up and the lights now appear like they're lower, that obviously tells you that you're going up and down.
Right.
Use an accelerometer.
Accelerometer is not being used right now. We use it only for maintaining the quad rotor in a position. All right. Man, so many questions at one time. Did I answer your questions?
No, but I don't want
All
to
right.
bring the class.
I'll actually have a lot more stuff in here later, and then we'll meet a lot. One last thing.
Can you tell which quadcopter is which using this, or do you need some other method?
Good question. Can you tell which quad rotor is which based on this? The answer is no. There would be another type, if you're using just this, and again, this camera only does the 4 brightest lights. You can kind of do little tricky things, and we had thought about this but didn't put it into place. For example, really what we care about are these 3. And this is just there for sometimes a reference. Well, what if you had one of the quad rotors, put it there, and one of the quad rotors put it over there, and one of the quad rotors put it up there, and one of them put it up there, and then you could just do other types of orientations too. But we haven't looked at that. Yes.
Have you tried the Keynet camera? Because I know some computer reader research use Keynet.
I have not used the key. You said the Keynet?
Connect.
Oh, Connect. Right. I use Connect for other things, but the Connect is so unbelievably heavy that I can't fly it. So if you've seen this quad rotor as it comes around, this camera is tiny compared to some of the other things. I mean, even look at this webcam right there. That's big compared to some of the other types of cameras that are out there. We are actually looking to move off to another camera because, as you are obviously mentioning, this is getting kind of constrained on its usefulness, and you can get a lot more data out of a regular camera that is fairly high precision versus this, which says you only get the 4 brightest points and that's it.
Right.
What kind of frame rate do you get? As far as could you multiplex and have one quadcopter drop every 8th frame and one drop every 16th frame of illumination, so illumination dropped on this one, that's number so and so.
And in fact, using some sort of pulse width modulation for the LEDs is another thing we had thought about, but we hadn't got to that point yet. I mean, you could by doing some sort of communication. And in fact, funny you mentioned that, I actually have another research paper that does that very thing. We have a camera and we have a flashlight, and we're saying, can the camera pick up a modulation of a flash shining on the wall to be able to see? Can you use it to pick up some sort of pulse with modulated signal? And of course, you're constrained by what?
Distance.
Speed of the camera, actually.
Right.
30 frames a second. You can't really do that much with it. Yes, sir.
There's been some work done on doing that with laser pointers. They had reasonable results.
Say that again?
There's been some work on that done with laser pointers. They seem to have reasonably good results.
Okay. And we were looking for our application calls something completely different, which would take an entire 1 hour to do on it. So yes, all great ideas. Man, all these things that we had thought about too, and some that I haven't. Let me go forward with some. So the thing to keep in mind is that when you have a typical quad rotor system, you have a complete flight system with its own sensors inside. And very often what you want to do is you want to use this interface here to pass along between, all right, this is what we have identified in our vision system. Based on this, these are the commands that I want to give you for our specific quad rotor. So in essence, we're trying to break this down into something really simple. The flight controller, remember somebody asked accelerometers, that would be one of these sensors as well. And based on our vision processor, which in our case has been switched between several different devices, everything from a Raspberry Pi to an Arduino to an Arduino Red board. This is the basic architecture of what we're doing. I already talked about the beacon. Oh, and by the way, one reason we also do a fourth LED is because this particular camera returns 4 of the brightest blips. And if you don't give it 4, it will find another one. And unfortunately, the other one it finds may not be really good for your working algorithms. So we really only care about B1, B2, and B3, but we give it B4 just so that we can saturate the camera so it returns a nice pattern that we know exists. And in fact, sometimes you don't know what you're going to get. So in this case, we're going to talk about using our Wii camera via I2C. And on the Red board itself, we're going to do the processing of the Wii camera data, send a pulse width modulated signal to a quad rotor for its instructions on how to move. Now, in particular, and this is the flight system. You can see this on the vehicles. We pass it around. I do not think. Let's see. Do I have the Red board on there?
It's that one.
Pardon me?
It's this one.
The blue board that's
No.
that you have.
No, yeah, that's on the top. This is the one on the top.
Yeah.
Did I put the Red board on that one?
No, I didn't.
Okay, so right now I have, these are the ones that we're building just before we put the Red board on it, because the Red board will be underneath the, the Red board will be on top of the flight system board, and I haven't put that one on yet.
The camera's not attached.
The camera should be on it.
It's not attached.
Oh, it's not attached, okay. Yeah, the camera would actually attach to the Red board on top. Let's see. Let me tell you about.
What IMU are you using?
Well, the IMU is the one that comes on this board itself.
What is that?
And I am not sure which one it is in particular. I am just a buyer of the product.
It looks like
But that's where it's at.
What does IMU stand for?
An IMU is an inertial measurement unit. Typically, an IMU has accelerometers on it, gyroscopes, sometimes compasses,
And altitude sensor.
and sometimes an altitude sensor, pressure sensor, sometimes. And it all depends on the particular unit. The nice thing about this is that all of those types of sensors are used by the main processor for its PID control, basically the control that keeps it hovering, and then you can give it the small little move it this way, move it that way. Is everybody familiar with how a quad rotor is able to maintain its flight anyhow?
No.
Or do I need to go into that? All right, let's go into that. So if you were to look at the quad rotor, and it looks like somebody did not put the blades on that correctly.
Yeah, the color and the arrow is not in alignment.
Yeah. You have, in fact, I think I have a slide on that. Okay, there you go. You actually have, I wonder if that is correct. We actually have, of the 4 propellers on your unit, 2 of the propellers spin in one direction and 2 of them spin in the other direction. Notice that this propeller is spinning clockwise, that one as well, the other one is spinning counterclockwise. Based on the ability of those rotors to spin at extremely high rates of speed, 4,000 revolutions per minute and up, you are able to maintain a fairly stable flight without much control needed. Control meaning that because that these are flying so, or these are spinning so fast, the aerodynamics are such that because of the inertia of the propellers themselves, the airflow. It does pretty good with maintaining its flight. The PID controller will allow it to modify the RPMs of particular propellers slightly so that it maintains a stable flight. Yes, sir.
It's totally unstable without the PID
Yes.
control of the accelerometers and the rate towers.
Correct.
So why have you gone with 4 instead of 6?
Cheaper.
I was going to ask if that's the only reason.
Because my goal was to make a swarm of 100 of these things. The more motors, the more it costs. The more hardware, the more batteries.
Okay, what is the advantages or disadvantages of the 6 over a 4, vice versa?
Safety. You can lose one motor and it'll still fly.
With 6, you mean?
Yeah.
Well, with 4, you're dead.
Pardon me? Yeah, with
With 4,
4 you
it's
lose
dead.
1, you're pretty much dead.
Yeah.
Really? You
Oh,
fly
we can't
on
shut
foot?
down
you
the
can't
second.
fly
They're
with
not
three.
reversible props.
And the other aspect of this too is my goal of this research was to create a swarm of relatively disposable vehicles, because the whole idea is these things are flying into buildings and you may never find them again. All right, I've already had the pain of losing one, right? And so that was really painful, and that was about as big as that one over there. That was $600. These are actually, I said 600 earlier, or 550. Actually, I think I priced these. They're more like 250 to 300, and I could start buying these in quantity and get it down to 150, because I've got now a supplier of most parts from China, where I can get things really cheap. I said 2 hands at one time. Let me go with you first.
I was just going to say something about losing one of the rotors. I saw a video one time where a guy was able to fly one of these things where he lost his 4th rotor, and he threw it in an interesting way where it spun around. Like he lost complete control of the rotation of it, and he was able to fly it in a completely different way where it was destabilizing one of its rotation. And it was really able to fly.
The unfortunate thing is that, but it's still not useful.
Yeah, I mean, you can fly it, like you can fly it, but
But again, don't forget, what I'm doing is these things are autonomous.
Yeah.
So once it loses one, it's gone. Once it nicks the wall or something like that, it's it may lose part of it. It's probably gone too. Yes, sir.
What's the useful payload on that?
I do not have that information off the top of my head, but these were able to fly for 35 minutes. With the additional weight on that is going to be the battery and the red board, and I'm not really sure, but you held that, and it's not all that heavy. And I think the battery again is about as much as that currently weighs.
So you're not planning on sticking out on that much more equipment then?
Yeah, I'm not putting that much more equipment on that.
Okay, thank you.
Yeah, there's no way this thing is carrying
bottles of water.
your latest book from Amazon, right?
Are people putting lawnmower engines on these things?
Well,
Again, these are flying, or each one of the motors is going at about 4,000 RPM, and so if anybody's doing that with a lawnmower engine, that's really, it's heavy in itself. So
Yeah. I don't think a lawnmower engine can go that fast.
even if you gear it.
You just use larger diameter.
Oh, that would be, wasn't it on MacGyver? Didn't he get an airplane glider thing, ultralight going with a lawnmower? That was disputed by MythBusters, if I remember correctly. So
sure.
There is a group of people that are using a single motor and then have variable pitch on each of the rotor heads. But they're just helicopter heads and modifying them. And that's scalable to a large.
and mind you, you've seen smaller ones of these. I showed you the video from UPenn had much smaller than these, and I've seen ones that are even smaller than that fly for quite a bit of time.
Yeah, there's one that's under $50 right now that has rate gyros and accelerometers, so it's totally stable. And You can get it at your local hobby center.
So going on, I just have a couple more slides. This is just a concept that I talked about earlier. This is how we're able to identify the correct flying. If you're at the same altitude, how you can identify where you are located with some of the math, as opposed to you can identify the sizes. Yes, sir.
Does the plane, as you're looking at here, does the plane of the camera relative to the plane of the sensors? I mean, is that significant or?
It is,
Okay.
because, you know, in the sense you're, it's a field of view,
Yeah.
and the width of your camera view is not going to be that much. And of course, the further you get away,
Yeah.
the less and less, or the intensity of the LEDs is not going to make that much of an impact for the camera itself. That's another reason why we're kind of going away from this Wii camera, because it's just a little bit too weak.
Yeah.
Is probably the best thing. Plus, the other aspect is we need a lens that's more focusable, so that we can at least try and change the field of depth and try and improve.
So you gotta write your own algorithm for finding the 3 infrared.
So we're going to
LEDs?
what?
So if you go to a different camera, then that means now you've got to write your own algorithm to find the 3 dots, right?
Believe it or not, that's easy.
Yeah.
That's
That's
there's
a lot of-
a software package
Yeah.
called OpenCV
I know what OpenCV is.
that has that runs on, for example, Raspberry Pis.
Yeah.
And we actually, I have done, my students and I have done quite a bit of work using OpenCV and that algorithm to identify the location, the size, the intensity of any of those types of dots.
But now if you put something that can run OpenCV on this thing, and you're putting a full-fledged computer on that,
Yep.
like a Raspberry Pi or a Beaglebone Black or something like that.
And you have enough lift capacity for that?
Nope.
If you're putting 10 anchors in the motor, you've got plenty of power for those.
Oh yeah, the power is no big deal.
I'm not
The
worried
problem
about
comes
the
down
power.
to the weight.
Yeah.
As you're adding more and more, as you're adding the bigger camera and a more beefy board, then you're now adding more and more weight. You know, the current consumption is not that much. The computational intensity, we've got to work on the algorithms to make it a little bit faster too.
The processor on a Pi doesn't weigh much more than the processor on an Arduino.
No.
It's a little bit of plastic.
But there is more weight because you've now got the SD card and
You don't need an
all the
SD card.
The weight of those connectors.
on a Raspberry Pi you do.
The
Yeah.
power, the power connectors on that thing that's been passed around could be optimized, and that would eliminate the weight difference.
Well, you got to choose.
Those DC power connectors that are like this
Yeah,
I should have you guys help me redesign. Yes, sir.
There's one thing up there is, I don't think that's formula is adequate. Because you're not going to be able to tell how far away you are until you measure that vertical distance.
Vertical distance, meaning.
The
You
fourth
don't have
dot.
to show the lens.
Oh, the 4th dot. Well, don't forget the
How the dots are a part of
where
it.
the dots are in your range of view, because if it's at the top versus at the bottom.
Yeah, but you don't know what your
You
what
can
your-
distance with 2.
I mean, theoretically, I would say you would turn your quadcopter so that the LEDs were in your center of view, and then you would need to measure the height from the bottom to the top to figure out the distance, which is the distance between the LEDs.
We're trying to do this as simply as possible. And so the assumption to begin with is everything is flying on the same plane. Everything is stable. You know, when we start getting into the fact that something may have a pitch or a yaw or a roll different than the other, we're working on those algorithms as well. So, you know, this is the first step. We've made the first baby step. As research goes, it's always good to be able to demonstrate something and then work on the next one and the next one and the next one. So
Change one parameter at a time.
Exactly.
It's been my experience in doing some contest work for indoor contests that a compass is worthless.
Compasses
So
are usually.
I'm concerned that you're gonna be able to keep your north, south, east, west parallelism.
Oh.
That may be on version 6.
I mean, take a very good idea.
He's got version 1.
Yeah.
He wants to move to version 2 later.
And again, you know, for example, some of the things that we're finding out is that this camera is not working as well as it could.
Yeah.
And so we obviously have to have something else. Perhaps we have something on a gimbal. Perhaps we have something that is controlled with a servo. That is going to be a lot better at identifying. In other words, having the camera move and not the quad rotor. Because if we want to maintain stable flight, you know, anytime we do a pitch, a yaw, or a roll, the whole thing moves, and now everything is not going to be consistent. All right, going on. I think I see some people glossing over. We tested this with a minimum of 20 inches and a maximum of 96, and it didn't matter if we had fluorescent lights on, lights off, sunlight. Made a little bit of difference sometimes, but it worked most of the time. But again, what we did find is that it didn't take very much movement of our vehicle versus the beacon to really make it not work well. So this was our some of our test environment for it.
So if you did have a camera looking down, holding position, you could probably improve your performance.
Correct. I mean, let's put it this way. If you had a camera being able to look in 360, you would be able to identify everything in its field of view that is of interest. So what's the next step to a 360 type of camera?
Spin the whole thing.
We're also looking at an extremely lightweight LiDAR.
Mm-hmm.
One of those that come on the top of the vacuum cleaners.
Yes.
So I've already talked about building a swarm with an eventual swarm, something that would look like this.
Have you thought about carrying in beacons that would be more? It would make your airworthy devices more useful if you just carried in a stick that had the light on. And just
you're saying if the vehicle carried below it a stick that had those lights.
that it could leave, and then another one could take it on to the next one.
Well, I mean, as I said, that's very similar to dropping the breadcrumbs.
Mm-hmm.
But actually, that just got me to think. What if I had a string of LEDs down that flew underneath the vehicle? Neat idea. That's why I like doing stuff like this.
I was actually doing what you're talking about 25 years ago with a lawnmower. As far as the beacon locomotion.
How'd you get that
lawnmower
lawnmower
was flying?
No, it's a lawnmower, but the multiple.
How'd you get it to hover?
Actually, I was just doing one at height and one at the bottom, and you could get the trigonometry to tell distance, and you need a head.
We had a question back there.
I can see one issue with the string of lights. If they're going into a broken building, it's going to get stuck on things. So, what if just like like they sell lights at Walmart that they're LEDs, but they have 3 that angle itself. So something like that would probably be better.
Yeah, one of the difficulties we have with any sort of light whatsoever is that typically an LED has a limited range of intensity. And so usually it's starting from the unit itself, it's like that. So even if I had something that was hanging down, I'd have to put multiple around so that it would still be visible in many different directions. So there's all sorts of options, and at this point we haven't investigated in great detail because right now our emphasis is to get a couple of these vehicles flying in swarms consistently, actually getting several of these things to fly consistently not in swarms, just go up, fly, and then land again.
Oh,
Which
no.
is autonomously, which is a lot harder than you can imagine.
Since you're probably working indoors and on a solid surface, would ultrasonic beacons work, ultrasonic sensors to maintain altitude?
We do use those,
Ultrasonic
yes.
sensor on the bottom of that one.
Yeah, there's an ultrasonic on the bottom and also on the forward.
There's one on the front, yeah, I noticed there.
Yes, sir.
You've mentioned before that it'd be nice to have some help working on this stuff.
They have some what on it?
Help working on this stuff. Is
Oh.
your hardware design open source?
Although everything is more or less open source, at this point, a lot of the hardware design that we're doing is a solved problem. Our big effort right now is to get the software running and the software working.
Okay.
So we're trying to buy off-the-shelf hardware solutions, maybe add a couple of sensors, but it's the software that's going to be the hard part. We had one back there, Rodney, and then you right here, sir.
You mentioned if you had a string hanging down multiple LEDs in different directions, you could have a single LED embedded in a clear piece of plexiglass, something like that, but it has reflectors. It reflects it out in multiple directions of an LED.
Okay.
That is more weight to carry, but it's easier to have multiple LEDs around the perimeter.
Okay, that's an idea. And yes, sir.
Have you looked at the state of the art in terms of inertial guidance, where basically the quadcopter keeps track of its movements, and it knows that it has moved 3.5 feet this way and so on, so that when you're using this reckoning system with the LEDs, and there happens to be a column in the building or something, you're losing the view. You're losing information. So I'm wondering. You're losing your guidance. I'm wondering if you've looked at using inertial guidance, using the precision accelerometers and so on, where it's available to track and know the relative motion of the quadcopter.
It's a good idea, and no, we haven't. I know some people have looked into it. It is not an easy problem.
No,
it's a lot easier when you have, quote unquote, a wheel on the ground, and we have kicked around the idea, but no, we haven't looked at it yet.
I mean, it would definitely add to your software burden. But
I mean, that's probably the best way to go.
Military aircraft, spacecraft, and so on. I mean, that's how they do it, right?
Ballistic missiles.
But they're not cheap.
And they have lots of wonderful gyroscopic devices, which
and funding.
But again, one thing that we're looking at is throwaway devices.
But there's, for example, I think it's ST makes a very high precision accelerometer gyroscope chip that is literally it's marketed as an inertial guidance mechanism that may be accurate enough, right? In other words, you're not going to be able to hit a target on the other side of the globe, but maybe you can determine whether or not you've moved a certain distance.
The controller that's on the larger one actually has that sensor on it.
It has the same kind of sensors, but it's
Well,
not.
it's a single chip that has 5 degrees of freedom. If you
That's
can
right,
figure out
but it's
what
not
that is.
doing inertial. It's using it to reckon and maintain orientation versus figuring out where it's not figuring out now. First it's here, now it's here.
Well, it knows how fast it's going.
Sure.
And the direction.
Absolutely.
So you could get from it that information because it is available as variables in the software. And the software is open source. So you could do a rough estimate of how far you've gone by using the data that's on.
So the answer is yes, we've thought about it. No, we haven't done any work on it because there's, again, only so much time of the day we have. All right, there were 3 hands at one time, and I don't know who was first.
I don't know. Go with them first.
Okay. So when you get to the point where you've got a swarm, and you're doing some more advanced testing, in terms of the path of the whole swarm, is that going to be, is the AI going to be centrally localized and commands distributed through communication? Or is it going to be something like a ant model of, or a swarm of swallows model of, how are you going to make those decisions and distribute the orders?
The expectation is that the control of a swarm will, and the swarms we're working are smaller, more like 9 units or so. The control of the swarm will be single one of the elements in the swarm, but each one of the other units in the swarm will have specific tasks to do. For example, 2 of the quad rotors on the outside will actually maintain or transmit information to everybody else about the distance from the walls on the side. One in the front will determine the distance to the front, one in the back will distance to anything in the back, another one looking up, another one looking down, and conveying that information to everybody else. But there will be one single one which will determine, all right, our mission says we must go this way, so let's all go that way. All right?
So is the perception then that one of these units could really do the processing or tasking to be able to fly through a building on its own? So you're using a swarm of them to distribute those jobs?
Correct. The expectation is that actually one of these swarms could have multiple jobs that it could do.
Mm-hmm.
For example, maybe there are 4 in a swarm that could do that one type of control of all the other ones. And maybe 2 of the units could look both up and down, and their selection is to do one or the other. But if it needs to be replaced, then it could take on that other job. The whole idea is that we're going to start with a swarm of 9. And the other aspect of this is what gets a little bit farther out there, is if we're dropping breadcrumbs along the way, that also allows us to have another unit come in from storage, follow the breadcrumb trail, and replace a new one. And when one of the swarms of 9 decides that he's tired and his battery is going down, he could drop down to the ground and become a breadcrumb.
Yeah.
And then the new replacements come in and take up the flight. Yes, sir.
Let me ask, what are you currently using for onboard processing?
Say that again?
You mentioned using a BeagleBone in the future. What are you currently using for onboard processing?
The onboard process, first of all, for the flight is the from RC Timer.
Mm-hmm.
And then the other processor that we're using is just the Wii camera. We have actually done some initial work with the Raspberry Pi for OpenCV, and that is actually the subject of.
Did you use their camera? Because they have an infrared camera.
Yeah, I'm trying to think if we used that one or another one. We used another one, and I can't remember off the top of my head what it was.
Because they now have their normal camera, but they've also just come out with an infrared version of that camera.
I did not know there was an infrared version.
Yes. All they've really done is remove the filter.
Fred,
I
you had a question?
think you answered it already. I was going to ask about the obstacle avoidance and path thing, but I guess it's kind of summed it up already.
And again, most of the interesting stuff is the final mission. What's going on. A lot of this, all right, let's maintain a swarm is interesting, but it's not the real, it's not what's going to sell this to the military. It's not the sizzle.
Is this document available somewhere?
Specifically, if you are a member of IEEE and you have access to this, this is described in this paper, maintaining and establishing and maintaining formations in mini quadrotors. There's also another paper which has been just published towards establishing and maintaining autonomous quadrotor formations in the ISYNCHRO conference. Yes, sir.
I have a question about swarm. So, what kind of algorithm are you gonna use for the swarm? Because I did a swarm research about 6 years ago, 6 or 7 years. There are all kinds of swarms for.
And as I discussed earlier, the swarm where you have flocking tendencies, where things go one way and the other way, and they're all independent but somewhat working together. My swarm is going to be, there's one controller, and again, since these are relatively autonomous, they are given a mission at the beginning, and they're given their own autonomy to find their way to succeed and do the mission, but there will still be one unit remotely which is determining the direction of the swarm. And each element of the swarm has its own responsibility and its own task. And one of those tasks may be to take image, light up the area, take an image, and then pass it back to the base station via that breadcrumb trail.
Yeah.
So again, the control of the swarm will be mostly mission-based, go this way, go that way, up, down, whatever. Relatively simple.
But the algorithm could be very complicated.
It could, but at this point, we're not. I mean, as you can imagine, there is so much work that one could do, but in the world of research, you take a little nibble and you document that fully, and then you take another nibble and you document that fully, and the whole hope is that you build on what somebody else has done.
So these are master's and undergraduate, senior projects?
Actually, these are master's and undergraduate only students working on this. Since I don't have full DoD funding or anything like this, I haven't been able to pay a PhD, which would greatly advance this work, and there's only so much time I have to work on this as well.
And you have to go to Charlotte.
Yeah, that would help. And that means I don't have time for this human robot.
Sure
sorry,
you do.
Man. But if you're here, you can work on a human robot, right?
Yeah.
Any other questions? Lots of questions. Lots of good ideas. And I wish I could have a nice video that would display all this working, but as it is for some reason, I keep on telling my students I want video. And, oh, it worked. It was great. You should have seen it. All right, great. Can you show it to me now? Oh, it doesn't work now. What did the video look like? Oh, we didn't remember a video. So, do I believe them?
On its cell phone.
Still
Come on.
That's positive belief.
Well, I think that's it, and I think I took a little bit more time than I should have. Oh, by the way, I think I showed all the way at the end. Here's my contact information. This is, I was recently in India, so that's a friend that I made in India.
Spiritual.
Spiritual friend, yes.
You have dynamics equations up there. Share that first.
I will, after I take this down, after some people are taking pictures. So.
Sorry, but that's not a really good time.
All right, thank you very much.